Good afternoon, and thank you for attending our webinar. I would also like to thank the folks at ACMA for this opportunity. Our presentation is about utilizing recycled fiberglass for affordable green technology. In the past decade or so, there has been significant focus on caring for and cleaning up our environment. Government agencies are mandating more stringent regulations on major issues like air emissions and fuel efficiencies. Our composites industry has contributed much to helping meet our lofty environmental goals. The employment of lightweight FRP designs has greatly improved both automobile and aerospace industry fuel efficiencies, while giving rise to an eco-friendly wind energy market. And I'd like to note that these industries have benefited greatly from the growth of carbon fiber technology. For example, the Boeing 787 Dreamliner. Ironically, these same FRP materials offering countless energy and environmental benefits have looming issues regarding disposal and reclamation. It's estimated that the global fiberglass output will exceed 4.8 million tons by the end of 2013. It's also projected that of that 4.8 million tons, approximately 400,000 tons of composite waste will be generated from manufacturing processes. And these estimates don't include existing FRP products reaching their life expectancy and design limitations. Faced with growing sustainability concerns regarding increased hazardous landfill costs and overburdening waste fiberglass inventories, FRP manufacturers are looking to recycling and reclamation as a solution. As in the development of all new and progressive technologies, the greatest driver or motivation for recycling FRP will always be cost. For example, there are disposal costs, which include transportation and landfill expenses, and opportunity costs, which are scrap materials that could have been used to produce saleable products. Presently, the three most common types of FRP recycling processes are mechanical shredding, incineration, and reclamation harvesting. The mechanical shredding method produces inconsistent reclaimed fiber sizes, resulting in inconsistent physical properties, while incineration is a very expensive process with high capital equipment costs. While this process burns off resin, it also degrades physical properties of the fiber. Reclamation harvesting, on the other hand, is a more reliable and consistent method of recycling FRP. It eliminates damages to the fibers from extreme temperatures and maintains more consistent sizing, which helps preserve the fiber's original physical properties. With respect to reprocessing and reusing recycled FRP, reclamation harvesting seems the most viable process. The big question is, what do you do with the fibers once they've been harvested? Presently, recycled FRP can be reused in various fiberglass manufacturing processes such as hand layup, compression molding, and pultrusion, just to mention a few. However, these methods have limitations regarding the volume of recycled FRP consumed, as conventional fiberglass methods consume relatively small volumes of recycled FRP. One economical and effective method of consuming large volumes of waste FRP is to exploit the reclamation harvesting method and incorporating reclaimed fibers into Solid-Cast-Polymer composite systems. This slide illustrates that conventional fiberglass components consume a greater percentage of recycled FRP waste than does solid-cast polymer. However, based on a similar square area, solid-cast polymer products consume a greater volume of recycled FRP because it's typically produced in greater thicknesses. So what is a solid-cast polymer composite system? Solid-cast polymer, or SCP as we refer to it, is an advanced composite material of construction that exhibits superior physical properties, corrosion resistant, and a multitude of other features and benefits. However, one of its most important qualities is its environmental value. Solid-cast polymer, or SCP, is a concrete-like material made from chemically inert mineral fillers such as quartz and silica sand, thermosetting polymer resins, and select reinforcing media in the form of recycled fibers, FRP fibers. Other than the silica quartz-based aggregates, which make up approximately 90% of the SCP, two key components in the solid-cast polymer matrix are the resin and recycled FRP. The SCP resin is a patented environmentally responsible thermosetting resin that does not contain volatile organic compounds or hazardous air pollutants. It's highly productive as it initiates faster curing, which increases output, and this resin system is non-flammable. The FRP reclamation harvesting process not only helps reduce fiberglass waste, it also lowers overall SCP raw material costs while maintaining fiber integrity and size consistency. More importantly, this process helps generate revenues by converting FRP waste into commercially proven solid-cast polymer products. Solid-cast polymer exhibits superior physical properties. For example, Portland cement concrete has a compressive strength of 3,000 to 5,000 psi. SCP is completely corrosion resistant through and through versus Portland cement concrete, which needs thin liners and protective coatings. SCP is also virtually impermeable while completely encapsulating the hazardous waste FRP fibers and resin. It's rigid, durable, and resilient, and can be reinforced with various materials It can be reinforced with various materials such as rebar, which facilitates lighter weight structures. The FRP reclamation harvesting process not only helps reduce fiberglass waste, it lowers overall SCP raw material costs while maintaining fiber integrity and size consistency. More importantly, this process helps generate revenues by converting fiberglass waste into commercially proven solid-cast polymer products. Solid-cast polymer exhibits superior physical properties. For example, Portland cement concrete has a compressive strength of approximately 3,000 to 5,000 psi. Solid-cast polymer is completely corrosion resistant through and through versus Portland cement concrete, which needs thin liners and protective coatings. SCP is virtually impermeable while completely encapsulating the hazardous waste FRP fibers and resin. SCP is rigid, durable, and resilient, and can be reinforced with various materials such as rebar, which facilitates lighter weight and stronger structures. Solid-cast polymer products are installed using two basic methods of construction: precast or cast in place. SCP products also have a broad market appeal, as these systems have been used in one form or another for over 30 years. SCP products can be used to contain corrosive chemicals like acids and caustics. They can be used in the refining of basic metals such as copper and zinc. But to date, its strongest market appeal has been in the sanitary sewer market, providing large diameter pipe, manhole structures, and tunnel lining systems. Still, a key and emerging solid cast polymer market is transportation and the replacement of creosoted wood and Portland cement concrete railroad ties. In this application, SCP demonstrates great strength, durability, and wear resistance. Solid-Cast Polymer has many features and benefits, but as it relates to the utilization of recycled FRP, its greatest benefit is its consumption of large volumes of waste FRP. This slide illustrates the volume of solid-cast polymer and recycled FRP used in a 1 mile span of 2 separate solid-cast polymer projects. As you can see, SCP can consume vast quantities of recycled FRP. Remembering that the greatest motivation for recycling is cost, we conclude that solid-cast polymer is emerging as a significant cost-effective alternative technology for recycled FRP, while always remaining environmentally responsible.